Welcome to this explainer, made by Forge College. I'm absolutely thrilled to be your guide today as we tackle implementing Borsh serialization for entry data. In our last lesson, designing a robust program entry point, we sketched out some really beautiful abstract ideas. But today? Well, today, we're trading our sketch pencils for some technical ink. We're going to draft a strict, compilable Rust blueprint for your capstone project, which of course sits right inside our module on building Solana program entry points. By the time we wrap up, you'll have a rock-solid, deterministic serialization strategy fully drawn up and ready for deployment. Okay, let's take a quick look at our blueprint for today. We're covering the entry point, parsing problem, diving into Borsh serialization, splitting up our headers and payloads, implementing that actual Rust serialization code, running some crucial round-trip tests, and finally, wrapping up with a summary and our next steps. All right, kicking things off with Section 1, the entry point parsing problem. So think of your program's entry point as the ultimate high-security vault's bouncer. This bouncer has one very specific job, and trust me, absolutely zero sense of humor. If a client hands over a slightly smudged ID, he doesn't ask for clarification. He just triggers a catastrophic runtime crash. Boom, done. As we saw previously, mismatches between the serialized layout and your parsing expectations are literally the #1 cause of failure here. The client thinks it's sending a totally valid instruction, but your program completely panics because it read the wrong byte. Abstract ideas are fun to talk about, but to actually survive on Solana, we need concrete, reproducible schemas. Moving right along to Section 2, enter Borsh serialization. To give our bouncer the perfect, foolproof schematic, we need a tool that eliminates all ambiguity. Enter Borsh. Technically, it stands for Binary Object Representation Serializer for hashing. But honestly, just think of it as the ultimate unforgiving VIP bouncer of the Solana runtime. Borsh strictly enforces deterministic encoding, rigid ordering, and fixed field layouts. It ensures that every single piece of incoming instruction data is predictably structured. And the best part? It beautifully balances keeping your transaction data extremely compact, which, saves you precious soul, with absolute parsing simplicity. With Borsh, there's absolutely no guessing. Field A is always followed by Field B. Now for Section 3, splitting headers and payloads. You see, our patent-style blueprint works best when we draw a hard line between two distinct spaces, the fixed front door and the variant-specific rooms. Over on the left, we've got the instruction header. This guy is fixed size, incredibly lightweight, and strictly used for lightning-fast action validation. Then on the right, we have the payload. This is the heavy lifter that handles variant-specific business logic and expandable vectors. This separation mirrors our dispatch flow perfectly. Your entry point can cheaply validate the header before it spends any of your precious compute resources unpacking a massive heavy payload. It's basically like checking the return address on an envelope before you go through the trouble of opening the whole package. All right, let's get our hands dirty in Section 4, implementing Rust serialization code. Let's literally ink this onto our actual Rust blueprint for the capstone project. Step 1, you're going to add the Borsh and Borsh-derive dependencies straight into your cargo configuration file. Step 2, cleanly define your header and payload structs in your instruction file. Step 3, implement your dispatch helper to make sure it reads that header first. And Step 4, write your round-trip tests. Seriously, ensuring this compiles without the compiler yelling at you is basically step 0 for any sane Solana developer. Here's what your header contract actually looks like in the code. We have an instruction header struct containing a version, which is just a 1-byte unsigned integer, and an action, another 1-byte unsigned integer. This delightfully simple 2-byte header is the absolute bedrock of our design. Now, you might be wondering why include a version tag. Well, it's so you don't accidentally break all your older legacy clients when you inevitably update your program down the road. Just 2 tiny bytes to completely secure the front door. Next up, we need a way to actually read this thing. Now, instead of just slapping a drive Borsh macro on the enum itself and calling it a day, tempting, I know, we're going to build a custom helper function called deserialize from bytes. This manually reads those first 2 header bytes right off the bat. If the length of the incoming byte array is less than 2, we've reject it immediately. Straight to the digital dumpster, no heavy lifting required whatsoever. We cheaply read the header, check the action, and only then do we dispatch to the correct payload deserialization. It is a massive win for both efficiency and security. Which brings us to Section 5, round-trip tests and hex checks. So we've drawn up the schematics, but listen, we aren't deploying a single thing until it passes quality assurance. This brings us to the absolute golden rule of serialization.
encode, then decode must result in the exact identical logical structure. We have to write round-trip tests in our test suite to prove our encoded Rust instructions bounce right back to their original values. If you create an initialized payload, serialize it to bytes, and then deserialize it, it better look exactly like the original. Because if it doesn't, our bouncer is going to get very, very confused at runtime.
Let's take a look at how the initialized payload physically occupies space on our binary blueprint. Down at offset 0, taking up exactly 1 byte, we have the version. At offset 1 sits the action. Then, starting right at offset 2 and stretching all the way to 34, sits the 32-byte owner public key. It is predictably anchored right there. You can literally look at a raw hex dump, pull out a magnifying glass, and point exactly to where the owner's key lives. That beautiful predictability, that's the absolute magic of Borsh. So how do you know your blueprint is actually perfect? You check off these 3 criteria. 1. Compilation success with your Borsh crates. 2. Round-trip equality successfully verified in your test suite. And 3. Perfect binary layout alignment when you inspect the hex. If you hit all 3 of those, congratulations! You have just successfully eliminated an entire class of nasty runtime errors. And finally, Section 6, Summary and Next Steps. Let's roll up our patent papers for a second and review this high-security vault we've just designed. Here are your main takeaways. First, treat that header as an unbreakable contract. You always want to prefer fixed-size headers for cheap validation. Second, keep your payloads compact. Think of fixed-length arrays like standard, predictable shipping containers. Third, use dynamic vectors, or vex, like expandable luggage, meaning only when absolutely necessary, because they add heavy overhead. And lastly, always write those round-trip tests.
Now that our schemas are rock solid, we are perfectly set up for our next phase: debugging and validating entry point handling. In that lesson, we'll focus on tracing a bad instruction from a raw, messy hex dump right back to the originating client call, so we can diagnose those really tricky mismatches. But before we go, I want to leave you with a bit of a puzzle. If your payload data completely doubles in size tomorrow because of some new feature you added, how exactly will your version tag gracefully handle the legacy clients that are still sending the old format? Think deeply about that backward compatibility as you finalize your entry points. This explainer was made by Forge College. Please make sure to visit forge.college to explore way more Web3 related topics and continue your programming with Solana journey. See you in the next one, and keep building.